Today we're going to talk about radians and degrees. Our goals are to learn some vocabulary related to angles, convert between radians and degrees, calculate the sector area and arc length, and learn something new, the linear speed and angular speed formulas. So let's get started with some vocabulary. We're talking about angles today that are on our XY coordinate axes. So we're going to talk about an angle in standard position. An angle in standard position will have an initial side. That one is going to coincide with the x-axis. We're also going to have a terminal side. So our angle is going to go some amount of degrees. Oops. It's going to go some amount of degrees, and it's going to end with a side. So our terminal side would be right here. Oops, let's make that red. Okay, so our terminal side is where our angle ends. Let's say this angle, it looks about 45 degrees, right? If we went all the way to the y-axis, that would be 90 degrees, and this is about halfway, so it looks to be 45 degrees. So when we go in this direction, counterclockwise, we're going to get positive angle measures. If I start at the x-axis and I go clockwise the other way, I'm going to get negative angle measures. Okay, now let's talk about this coterminal angles. Coterminal angles have the same initial side and terminal side. So they're different angles that start and end in the same place. So we have two main options. One is to have another positive angle that starts and ends in the same place. So that would be, I'm going, I pass the terminal side and I make a full loop, a full 360-degree loop, and I come back and I end in the same place. So if our original angle is 45 degrees, our blue angle is going to be 45 plus the 360 we went around. So that would be 405 degrees. Okay, and we're going in a positive direction. We have another option, which is to make a negative angle. So we're going to start at the same place, but we're going to go in the negative direction and meet around in our original place right here. So this is a negative angle, and this angle goes from here. We pass the negative 90-degree mark, the negative 180-degree mark, the negative 270-degree mark, and then we add another 45 degrees. So that would be negative 270 degrees plus negative 45 degrees, and I'll get something like negative 315 degrees is this angle that goes the other way. So those are all coterminal angles. They start in the same place and they end up in the same place. Okay, so we can do this without even looking at an axis. We can find two coterminal angles for negative 36 degrees and for 13 pi over 6. So at negative 36 degrees, I'm just kind of going to estimate where that is. That's going to go in a clockwise direction because it's a negative angle. And I'm going to estimate that to be like right about here because 45 degrees would be halfway in between both those axes. So this is a little bit less than that. So this is my angle here. Now my options are I could have a positive angle that meets all the way around. So that angle would be 360. We'll start from 360 if I went all the way here, but then I need to subtract that 36-degree angle. So I have one option, which is 360 degrees minus 36 degrees, which is something like 324-degree angle. Now my other option is I could still go in the negative direction, but I could just make an extra 360-degree loop before going back to that negative 36 degrees. So that would be negative 360 plus my negative 36-degree angle. That would be negative 396 degrees. Both of those angles will start and end in the same spot. Now I'm looking at 13 pi over 6. So if I draw a little axes, and I draw, where's 13 pi over 6 going to be? So I know a full circle is 2 pi. So 2 pi is going to be 12 pi over 6. So I need to go 1 pi over 6 further. So this is where my terminal side of my angle is going to be. My initial side is the x-axis. So I need to think of two angles that will get me the same result as 2 pi over 6 plus pi over 6. So I can already say right here, starting from 0 pi to pi over 6 will get me the same start, or my same initial and terminal sides. I can also think about a negative angle. So if I start at my x-axis and I go all the way around this way, almost 2 pi, but I'm leaving out this pi over 6. So I can write that as 2 pi minus pi over 6. I can just make my bases the same. I can say that's going to be 12 pi over 6 minus pi over 6. And I'll get that that angle is negative 11 pi over 6. Remember, because we're doing a negative angle here. Okay, now we're going to talk about finding complementary and supplementary angles. So if we remember from Math 2, complementary means that there are two angles that add up to 90 degrees, and supplementary means that there are two angles that add up to 180 degrees. So they're asking us about the angle 3 pi over 4. So 3 pi over 4, I know that this is 0 pi here on my x-axis. This is pi over 4 here. This is pi over 2, or 2 pi over 4. So this angle here is 3 pi over 4. Okay, so they're saying with this angle right here, what angle will be complementary to that? So what angle, when added to this, will equal 90 degrees? Now here's the thing. 90 degrees would be this angle right here. So we're already past that. So we're going to have a negative angle here to add in order to get this to equal 90 degrees. So with what I know about the unit circle, I know that this chunk is another pi over 4. So if I subtract pi over 4 from 3 pi over 4, I'll end up with my right angle. So my complementary angle would be negative pi over 4 because I'm going this way. I'm backing it up. I could also solve this algebraically. I know that 90 degrees is pi over 2 from just what I know about the unit circle from last year. So that means I need my original angle, 3 pi over 4, plus some other angle to equal pi over 2. Now what I can do is I can solve for theta. I can solve for my angle just like I would solve for x. So that's going to cancel out over here. And on this side, I want to make sure that I have the same denominator. So I can convert pi over 2 into 2 pi over 4, subtract 3 pi over 4, and I will get negative pi over 4 on this side. So my final answer is that the angle that's complementary to 3 pi over 4 is going to be negative pi over 4. So it's just another way of getting the same answer up here. Now similarly, when I'm looking for a supplementary angle to 3 pi over 4, I'm still looking at the same angle, 3 pi over 4, and I'm saying what's going to make that equal 180 degrees, which is this flat line. I have 3 pi over 4 here, and supplementary angle, 180 degrees, is just going to be 1 pi. So I can think of this the same way, supplementary. I have 3 pi over 4 plus some angle that needs to equal pi. Now I can convert them to have the same base. Pi can become 4 pi over 4. I will subtract 3 pi over 4 from both sides, and I'll end up with theta equals positive pi over 4. Okay. Now we're going to talk about converting radians to degrees. So this whole next few steps, I'm just going to use proportions. There's some more complicated ways to talk about it, but I'm just going to talk about this with proportions. So if I have a full circle, I know two things about this full circle. I know that all the way around, the full angle here, in degrees, that's going to be 360 degrees to go all the way around. And in radians, it's going to be 2 pi radians to go all the way around. Okay. Now, if I'm looking at this angle, just by looking at it, it's a right angle. I can tell it's 90 degrees. So I'm going to put over here my degrees measurements. My angle is 90 degrees, and all the way around is 360 degrees. Just by looking at that shape, I can tell that this angle, this chunk of the circle, is 1/4 of the circle. Now that makes sense. 90 divided by 360 will simplify to 1/4. Now it's 1/4 of the circle in degrees. My circle is still the same circle. My angle is still the same angle when I'm talking about it in radians. So that's still going to be 1/4 of 2 pi radians. So I can put 2 pi down here because that's my whole value all the way around. Oops. And I can solve for my angle up here in radians. So what I'm thinking about here when I build this proportion is my main idea is part over whole, right? This is the same fraction of the circle no matter what measurement we're talking about. My part is 90 degrees. My angle out of the entire circle, 90 degrees out of 360. In radians, we don't know what it is yet, but it's something out of 2 pi. So this is just my degrees side, and this is just my radian side. So it's important that I keep the degrees on the same side and my radians on the other side. Now I can use whatever I want to do. I can cross multiply, or I can just think about solving right here for my angle. To get rid of that, I can multiply by 2 pi on both sides. Okay, this is going to simplify into theta equals, my 2 pi is going to cancel out, 2 pi times 90 over 360. Okay, I already know that this simplifies to 1/4, so I have 2 pi over 4, which simplifies to pi over 2. And when I look at my unit circle, that checks out. I remember that this angle up here is pi over 2. Now again, we can use this same method going from degrees to radians or radians to degrees. It doesn't matter which way I'm going, and I don't even need to do a drawing the whole time. So let's start with converting 135 degrees into radians. Okay, so I'm going to set up my degrees side of my proportion. This is 135 degrees out of a full circle of 360 degrees. I'm going to set that equal to my radians over 2 pi. I'm going to do the same thing. I'm going to multiply both sides by 2 pi to solve for theta. Now I can simplify this in any way that I want to. If I had a calculator, honestly, I would just plug it in. I'm going to leave the pi there though. I'm not going to multiply by 3.14. That way we're more exact when we actually use the character for pi instead of substituting for 3.14. So if I didn't have a calculator though, I would just look for easy things to cancel out. 2 in 360 simplifies to 1 over 180, and I still have pi and 135 on top. Now I'm thinking I can divide 180 by 9 and 135 by 9. When I do that, I get 15, still pi, over 20. I can simplify both of those by 5, and I get 3 pi over 4. Nice angle right there. Okay, I'm going to do the same thing with 3 pi over 2, but that's a radian side. So this time I'm actually solving for my degrees. So x over 360, because I don't know what my angle in degrees is, equals, and then I'll put 3 pi over 2 up here as my angle in radians over 2 pi. Okay. Now this one's going to take a little bit of simplifying. I don't like mega fractions like that, so I'm going to simplify that first. That's going to be 3 pi over 2 times 1 over 2 pi. This is how I'm simplifying the mega fraction. So right away, I see that the pi's will cancel out on both sides, and that will leave me with 3/4. So I can say this whole mega fraction is equal to 3/4. Okay, so now I have x over 360 equals 3/4. I'm just going to multiply both sides by 360 in order to cancel out the denominator there. I'm going to think about the fact that I can cancel out 4 and 360. I know that simplifies to 90. So x equals 3 times 90, and 3 times 90 is 270 degrees. Okay. Now, they didn't just give us 4 for this third one. If they gave us 4, how would I know if it was radians or if it was 4 degrees? So that's why it says 4 rad. We don't need to say rad after 3 pi over 2 because we're assuming that 3 pi over 2, since it has a pi in it, is a radian. Also, with degrees, they'll always give us the degree symbol afterwards. So 4 radians. Okay, so I don't know my angle in degrees. I'm looking for my angle in degrees. And they give us 4 radians out of 2 pi radians. Okay, again, all I'm going to do, simplify and cross multiply. So I have x equals 4 times 360 over 2 pi. Now the 4 and the 2 can cancel out to 2. And up top, I will get x equals 360 times 2 is 720 over pi. Weird looking, but I'll take it. Now, negative 120 degrees. Oops, by the way, that's in degrees. So we can do this with negative angles too. I know that it's negative 120 degrees out of 360. And I don't know how many radians that is, so I'm going to solve for theta, which is how we represent x for angles in radians. We usually use theta instead. Okay, so now I'm going to multiply both sides by 2 pi. This cancels out. Okay, I have theta equals negative 120 over 360 times 2 pi. Again, I can simplify. Negative 120 over 360 is going to simplify to negative 1/3. So I can say I have theta equals negative 1/3 times 2 pi. And I can simplify that again to say theta equals negative 2 pi over 3. Perfect. Now we're going to talk about arc length and sector area. Okay, the book has some fancy equations. S equals r times theta, and A equals 1/2 r squared times theta. S stands for arc length, r stands for radius, theta is an angle in radians. A is for sector area, equals 1/2 radius r squared times theta, which again is our angle in radians. So the important thing to know about these two formulas is that the angle has to be in radians in order for this to work. So if they give you an angle in degrees, you would have to convert it into radians first in order for these two formulas to work. So I don't like to use the formulas. I like to think about this again in terms of proportions. So if I'm looking at this circle, they've given me x equals 210 degrees. And by the way, when we're looking at proportions, it's totally fine to use degrees or radians in proportions. We don't need to convert from one to the other if we use the proportion method. So back to the circle. They've given us this angle of 210 degrees. Okay, I'm going to start my proportion for arc length. 210 degrees out of 360 degrees. So this is 210 parts out of 360 parts total. Okay, arc length is the circumference, a part of the circumference. The circumference is the distance around the entire circle, but our arc length is the part of the circumference that attaches to the initial and terminal parts of our angle. So if our angle is 210 degrees out of 360, what we need to do is calculate our our circumference, and figure out 210 out of 360 parts of that circumference. So our circumference formula is 2 pi r, or pi d if you learned that way. So let's give us a radius of, how about 3? Our radius is like 3 centimeters. So in that case, our circumference is going to be 6 pi. So what I want to do is solve. I'm still going to use S for arc length. S is for arc length, or I could just write arc length or whatever variable I want there. I'm going to solve this proportion to figure out what fraction of that circumference is my arc length. All right, if I solve for S, I'm going to multiply by 6 pi on both sides in order to get S alone. It cancels out here, and then we're left with S equals 210 over 360 times 6 pi. So now I'm just going to do simplifying as much as I can. I can simplify this part of the fraction to 21 over 36 times 6 pi. I know that I can divide 6 by 36, and I'll be left with 1 over 6. So this is now 21 pi over 6. And I know that I can divide 21 and 6 both by 3. When I do that, I'll be left with 7 pi over 2. So my arc length is 7 pi over 2. Okay. Now for sector area. Sector area is very similar. We're still going to think about it as a proportion, but it now is a proportion of the area of the entire circle. So if we're thinking about a pizza and our arc length was the crust, the sector area is like the actual pizza. It's the slices of pizza. So it's still proportional. I'm still going to have 210 degrees out of 360 degrees, but I'm just going to ask myself what fraction of the area belongs to this sector area. So instead of using the circumference down here, I'm going to use my area of the circle. My area is pi r squared. If our radius is 3, we now have 9 pi as our area. Okay, so again, if I had radians, I would just plug radians over 2 pi on the left. Now, what I'm going to do is I'm going to solve for area, so I'm going to multiply both sides by 9 pi. These will cancel out, and I will end up with area equals 9 pi times 210 over 360. Okay, we already found out that we can simplify this to 21 over 36. When I think about that, I have 9 pi times 21 over 36. When I divide 9 by 36, I'm left with 1 over 4. So finally, I have A equals 21 pi over 4. I cannot simplify that further. My units are squared because this is an area. 21 pi over 4 is the sector area of this circle. Okay, so if you know those formulas from before, you can use the two formulas that I have up here. But I think it's much easier to visualize and use proportions to solve these types of problems. Okay, lastly, something new, we're talking about linear speed versus angular speed. So linear speed, if I've got a circle like this, my linear speed is how fast is something traveling, how fast is something traveling around the circumference of the circle, like this, right? I could unroll the circumference of the circle and visualize it this way. How fast is something moving along that line? Now my angular speed is just asking me how fast, I can't draw this. How fast is an angle moving at any certain point? So like you can think about a car tire. How fast is this angle moving if the car tire is rotating? So I think this is mostly easier to understand when we do some examples, but let me break down the formulas for you. Linear speed is right here. V equals S over T. V is our linear speed. S is still our arc length. And T is our time. Angular speed, that's this thing, this little W looking thing. Angular speed is our angle over time. Okay, so let's do some examples. It says the second hand of a clock is 10.2 centimeters. What is the linear speed of the tip of the second hand? So I'm just going to draw this out. We've got a clock here, and we have the hour hand, which is the short one, and then we've got the second hand, which is the long one. And it's telling us that the second hand is 10.2 centimeters. Okay, we can imagine it, right? Tick tock, tick tock, tick tock, going like this. So it's moving all the way around the circle, and we're going to move all the way around the circle. That's the only kind of like time I can break this problem down into, right? I know that it takes the clock a full 60 seconds for the second hand to go all the way around, because that's how long a minute is. So if I'm looking for my linear speed, I know that the time frame that we're talking about is 60 seconds. Okay, my arc length. At that point, if I'm talking about 60 seconds, I'm talking about the entire circle. So my arc length, I'm really not finding an arc length, I'm finding the total circumference, since my angle there is 360 degrees. If they gave us a different problem where they were kind of giving us a chunk like this, then I would go ahead and find the arc length using the proportion method. But right now, we're just talking about the circumference of the entire circle, since we're going all the way around the circle. So circumference is 2 pi r. My radius is 10.2 because that's how long the second hand is. All I would do now is simplify this in order to get my linear speed. So I can simplify, well, you know what? If we just give our answer in minutes or seconds, we'll have a different answer. So I'm going to go with seconds. So what I'm going to do is I'm just going to do 20.4. I multiply the 2 and the 10.2. Pi over 60 seconds. And the top is in centimeters. When I use a calculator, I would either get, if I leave the pi in, 0.34 pi centimeters per second, or I could simplify by multiplying by pi, and I'd get like 1.07 centimeters per second. Now this last problem, the blades of a wind turbine are 116 feet long. Okay, a wind turbine is that thing that you might see in the desert It looks like this, a giant propeller, and the blades spin around and around, powered by the wind. So they're saying one of these things is 116 feet long. So that looks like, right, they're going to spin in a circle. 116 feet seems like our radius. The propeller rotates at 15 revolutions per minute. Okay, 15 revolutions per minute. They're asking us to find both the angular speed in radians per minute and the linear speed of the blades. Okay, let's start with the angular speed. They're asking us for the angular speed, which we know is some angle over time. Now, originally, you might think to look at our angle here, but we're not talking about that. They didn't specify that there's 3 or 4 or 1 or 2 blades on these propellers. They're telling us, we're just using the information they've given us, 15 revolutions per minute. That means that we do a complete circle 15 times every minute. Okay, 15 times every minute. So I'm doing 2 pi, because we're talking about radians, they're asking for radians. I'm doing 2 pi as an angle, but I'm doing that 15 times per minute. So really, I'm going 30 pi per minute. So our angle here is 30 pi, and our time is 1 minute. 30 pi feet. Sorry, not feet, because we're talking about an angle. 30 pi per minute. This is radians. Okay, so that would just be our final answer, 30 pi radians per 1 minute. If I'm talking about finding the linear speed of the tips of the blades, okay, that's a little bit different. V equals S over T, where S is our arc length. Okay, again though, I'm talking about going through this 30 pi times. Okay, so my angle, if I'm talking about arc length, we have to find our arc length first. My angle is 30 pi out of 2 pi. Yes, that is much more than 2 pi, so we're expecting a big arc length here. Our original circumference is going to be 2 pi times 116. And we want to find what is this arc length? What is S in order to plug it in up here? So I'm going to spare all my calculations. When I multiply all of this together, I get that S equals 3,480 pi. So if I plug that into my equation, 3,480 pi, and the time frame it takes to go this whole time is per 1 minute. If I multiply out the pi, I get something like 1,933 feet per minute. Okay,